This video is on section 4.2, measures of dispersion. All right, little screen. Oh, there we go. Okay. The range is the difference between the largest data value and the smallest data value. We worked with the range when we were calculating class width. So recall, class width for quantitative data was the max minus the min, and then you divide by how many classes you wanted. So the range is the top of the class width formula. It is the max, largest value, minus the min, smallest value. So for example, if we were to calculate the range of the following data set, consisting of the number of times the television channel was changed in a 1-hour time span, it is easiest to identify min and maxes when you first order the data set. Especially if this was a much larger data set, it is very easy to miss a value in a large data set. So if we reordered this, we would then see that 1 is our minimum and 24 is our max. This is a very small data set, so it's pretty easy to see without reordering. Therefore, the range is 24 minus 1, which equals 23. Now, there are many times where the range really tells us nothing. So for example, let's say I gave a test in this class and someone doesn't show up for the exam and gets a 0, and another student shows up 8 is it. So my max grade is 100, my minimum grade is a 0, 100 minus 0 is 100. Okay, so now here I am telling you that, okay, the range of the grades on the test is 100 points. Well, did that really tell you anything? No. Before you guys even took the test, you knew there was a possibility of a 100-point spread. So in some cases, the range is meaningless. It really doesn't tell us anything. But if everybody took the exam and the lowest grade on the test was a 60 and the highest grade on the test was an 80, then if I told you that the range was 20 points, that tells you that everybody got within 20 points of each other on the test. That has a bit more application than 100 points, which is the entire range of grades to begin with. The variance of a data set containing the complete set of population data is given by the following formula. New symbols for us to add in, so let's do some labeling. Okay, so this symbol here we already know. We know the sum symbol. Okay, so this fancy E, remember, is the sum symbol. It means add this up. Add whatever is after the sum symbol. So here, the xi's, which we really don't need to read this formula because we're going to calculate variance and standard deviation in Rguroo, but still good to be able to read math. It kind of levels up our confidence when we are looking at formulas and reading a math book. Xi is just talking about the data values. This is mu. It told you the way I write it and the way that the computer types it. So this is mu. They look completely different. Mine kind of looks like cursive M's, and when they're written in type, it looks more like a U. But remember, this is mu. We talked about this in 4.1 when we were talking about location, measures of location. And this is the population mean. Right. Okay, here we go. Population mean. Yay. This big N, we talked about this in my last video of 4.1. Big N represents the population size. I'm going to abbreviate population, POP, population size. This guy is called sigma. Specifically, it's sigma squared. So sigma is what to me looks like a pregnant R. Plus, I think it's cute calling it a pregnant R. But others see it as more like an O with a little hat or a little tail coming out of it. But that symbol is called sigma. Now, sigma squared, because it's raised to the second power, is our population variance. Now, what the heck is a population variance? We haven't really gone into that. And in intro to statistics course like this one, we don't really dive into variance all that much. We handle standard deviation is a much more popular statistic or parameter. In this case, it's population, so it would be a parameter for us to work with. Now, one thing I wanted to keep these formulas in this lecture for was to show you that there is a difference for the first time. There's a difference in how you calculate variance for population than there is for a sample, which will be on the next slide. Now, that's different from when we introduced means. The population mean, mu, and the sample mean, x bar, they had the exact same formula. No difference in calculating. You just needed to know which symbol to use based on, did you have every data value from your target population, or did you only work with some? Now the sample variance, notice a small difference in the formula. Instead of dividing by just the sample size, such as in the population variance, we just divided by big N. Now we have to divide by N minus 1, which means the number is going to come out different even if we use the same data set. So you need to know if the data set is a sample or a variance, because a sample or a population, because the variance value will be different in the calculation. Okay, so again, you have your sum symbol. You have your xi, which is just saying you're going to do this calculation for every single data value in the set. X bar, we introduced in the 4.1 video, the measures of location. X bar is the sample mean. Little n here, recall that's the sample size, how many data values in the sample you took from the population. And S, really easy to remember sample variance, because sample variance is S squared. S for sample kind of works out. Okay, so S squared is sample variance. Again, if you're like, I don't know what a variance is, that's okay, because we haven't really covered what it is yet, nor do we really care as much as we care about the standard deviation. Given the following times in minutes of a 6-person running a 1,000-meter course, compute the sample variance. Okay, I'm going to jump to Rguroo so we can practice this. So we are going to create a very easy small data table in Rguroo using these values of 5, 10, 9, 11, 9, and 7. And I'm going to show you how to grab your summary statistics when you're just working with one column of data. So let me stop sharing this PowerPoint, and I am going to jump over to Rguroo. If I can find my screen with it. There we go. This is it. Nope, that is my email. We do not want my email sharing. Scratch that. Let's try this again. It's a process. Hopefully this is not my email this time. Ah, yay! Okay, so let me exit out of here. This is what we were working on in the measures of location lecture. So we sign in, go to data, then you're going to want to import data, create a new data set. Now, the variable, I forgot what the variable was even in the thing. It doesn't matter. I'm just going to leave it as variable 1 because I forgot what the data set stands for. And I am going to put in, we had 6 data values, so I need 6 rows. And the values were 5, 10, 9, 11, 9, and 7. I need to save this. This is going to be saved, and I'm going to name it what I'm trying to show, which is sample stats, sample statistics. Save as. Okay, now again, I personally feel comfortable to make sure it correctly got created. So I am going to double click on it in my list. Make sure again, my labels and my data values. Now there's 2 ways to get the sample statistics. We can go up to functions and hit summary statistics and select the data set, or we can just right click and select data set summary. So in my data set summary, remember Q2 is the median. So the middle value of an ordered data set is 9. The mean is 8.5. The standard deviation, which we haven't covered yet, is 2.168. And here's our variance, 4.7. Now, if you were doing the homework and you have to actually read the problem, does the problem say that this is a sample or it's a population? So that's how you would know to label this with sigma squared or labeling it S squared. And this is sample statistics, so everything in here is actually S squared. It's not a population of data. If it was a population, I actually don't know how that changes. Let me see in the screen if there is a way to select that summary statistic instead of parameters. I am going to have to look into that if it is a population data set, how to get Rguroo to calculate the population variance, because remember the formula is different. So I'll look into that one. Now let me jump back to the PowerPoint. Here we go. Okay, and as you see, they calculated the mean is 8.5. And I left the slide in here where they're doing the workout by hand, but please use Rguroo. Do not do this out by hand. Most of the problems we work with are sample, so we shouldn't have any issues with the Rguroo. Okay, so the average squared deviation is the data 4.7 squared minutes. This is a good explanation on why we don't really use variance that much. So the phrase squared minutes in the last sentence may seem a bit odd. No one carries out transactions in squared minutes or squared dollars or square tons. So it is difficult to interpret the significance of the measurement in this form. This is exactly why we are going to use standard deviation way more often. Standard deviation is the square root of variance. Okay, so let me write that out in symbols. And we're going to cover standard deviation in much more depth in a future section. But just so that you've heard it for the first time now, standard deviation, so the population standard deviation, this is the common abbreviation, STDEV, is the square root of the variance. So it's the square root of sigma squared. As we just learned, sigma squared is the symbol for population variance. So population standard deviation is just sigma because you square rooted the square on the symbol. And sample standard deviation is the square root of the sample variance. So S squared, which gives you the symbol S. Lowercase s is the symbol for sample standard deviation. Again, we will cover this in another lecture in much more detail. Or in this one. Guess I didn't remember it was in this one. Okay, standard deviation is also a measure of how much the data values vary around the mean. It is found by taking the square root of the variance. And standard deviation helps us determine the spread of the data. So if we have a very large standard deviation, we're going to see a very long curve. If we have a small standard deviation, we're going to see a very tight knit curve, very closely compact curve. The standard deviation is always non-negative. We're not using the word positive because 0 is not positive or negative. Okay? But non-negative means that 0 can be a standard deviation, but standard deviation cannot be negative. It is 0 only if all the data values are exactly the same. So if I gave you guys an exam and every single person got a 90 on the exam, the standard deviation would be 0 because no data values deviate from the mean. If everyone gets a 90, the mean is 90, there's no deviation. The standard deviation can increase dramatically if there are one or more outliers in the data. And we talked about that when we said that the students were all in the 70s and then you had that 100, or all in the 70s and had that 0, the mean will be directly affected by an outlier. The standard deviation is expressed in the same units as the original data values. So if we're talking about heights, then standard deviation is in the same unit. So let's say the heights were in inches, then standard deviation is also in inches. While variance is in inches squared, which, unless we're talking about area, it's really kind of hard to talk like that. Okay, the empirical rule. Empirical rule, if the distribution of the data is bell-shaped, then about 68% of the data values should fall within one standard deviation, 95 fall within 2, and 99.7 would lie within 3 standard deviations. Let's do a quick example. Actually, let me switch over to the whiteboard instead. Give us some more room. Here we go. Let's say that I gave you guys an exam and I told you that the class mean, the average exam grade was a 75 with a standard deviation of 5. Okay, again, we haven't really looked at calculating standard deviation or comparing it or really doing a lot of digging in it yet. But let me show you, the empirical rule really does help visualize what standard deviation is telling us. And I'm also going to tell you that the data is normally distributed, either normally distributed, symmetric, bell-shaped, all mean the same thing. Really important to remember, the empirical rule only works when the data is normally distributed. So our bell-shaped curve looks something like this. And we're going to label the mean of a normally distributed data set. A symmetric data set is always in the center. Now I'm going to label my standard deviations as I go out farther and farther to where the curve gets small. So here is my first standard deviation. And in order to calculate that, I'm going to take X bar plus a standard deviation. So we are going to have 75 plus the standard deviation of 5. So my first standard deviation comes out to 80 on the right side. And I'm going to do the same thing on the left side. I am going to take 75 and subtract a standard deviation because I'm going to the left side of the number line. I'm going to get a 70. The empirical rule tells me that 68% of the data values falls within one standard deviation about the mean. So I now know that 68% of the class got between 70 and an 80 on the exam. 68% of the class, or 68% of the grades, were between a 70 and an 80. That says a lot. Over half the class between a 70 and an 80. Okay. Let me erase this out of the way so we have a little bit more room. Now let's go out another standard deviation. So let's pop out and let's take one more standard deviation out. We're going to take the 80 and add another 5 to get 85. And I'm going to take the 70 and I'm going to subtract another 5. We're subtracting 5 because that's our standard deviation. I get 65. Now, according to the empirical rule, 95% of the data values fall within 2 standard deviations about the mean. So I could say that 95% of the data, or of the grades, falls within 65 and an 85. So 95% of the class got between a 65 and an 85, between a D and a B. That says a lot to me. Let's go out one more standard deviation. No, I lost my curve. I'm gonna have to draw that back in as I was erasing. I'm drawing my lines. Here we go. So I'm going to go out one more standard deviation out on the right and take 85 and add another 5 to get 90. Another standard deviation on the left to go 65 minus 5 to get 60. And now the empirical rule tells me that 99.7% of the data falls within 3 standard deviations. So I would be able to conclude that 99.7% of the class, or of the grades, fall within a grade of a 60 and a 90. So almost everyone got between a 60 and a 90 on the exam. Where is the other 0.3%? The other 0.3% are the outliers. So those who got, for this particular data set, it is telling me that if a student got more than a 90, that is very unusual. And it's also telling me that if a student got lower than a 60, that is very unusual for this data set. Let's head back to the PowerPoint now. So let's suppose a group of high technology stocks has an average earnings per share of $6.26 with a standard deviation of $1.37. If the data poses a bell-shaped distribution, which is another way of saying symmetric, which is another way of saying normally distributed, which interval contains 68% of the earnings? Which interval contains 95%? Okay, let's talk about this. So we know that 68%, according to the empirical rule, as long as the data is bell-shaped, which is clearly stated in this problem that it is, 68% of the data falls within one standard deviation. So if we were looking at this bell, we would put the mean of $6.26 at the center. And in order to find where 68% of the earnings would fall, you have to take $6.26 and add $1.37 to that. So if we get our handy dandy calculators, we're going to take $6.26 plus $1.37, and that gives us $7.63. Now I want to find the first standard deviation on the left side, so I'm going to take $6.26 and subtract the standard deviation of $1.37. And that gives me on the left side the first standard deviation being $4.89. So now I would be able to say that 68% of the earnings fall within $4.89 and $7.63. Now, where's 95% of the earnings? Well, we would take $7.63 and add another $1.37, which is the standard deviation. So going out one more standard deviation, we would get, let me get this out of the way. Slow erasing, there we go. We would get 763 plus 137 is $9 on the dot. 489 minus another $1.37 gives us $3.53. Oh, sorry, 52 cents. There we go. So now I would say that 95% of the earnings fall within $3.52 and $9. The proportion of, oh, this is Chebyshev's theorem. Okay, so the proportion of any data set lying within k standard deviations of the mean is at least 1 minus 1 over k squared for all k greater than 1. So if k was 2, at least 1 minus 1 over 2 squared, or 3/4 or 75% of the data values lie within 2 standard deviations of the mean for any data set. So why do we have two theorems that are talking about percentages of data within standard deviations? Because Chebyshev's theorem does not need a normal distribution in order to be used. The empirical rule, which is what we just covered with the specific 68, 95, and 99.7, absolutely has to be working with a symmetrical data set. So if k was 3, then using the same formula, we would have 1 minus 1 over 3 squared, or 8 over 9, which in percent form translates to 88.9% of the data values falls within 3 standard deviations. So k tells you how many standard deviations you're looking for, and this is going to calculate that percentage for you. So for example, the age distribution histogram for New Jersey in 2017 is shown in the graph. The mean of the data is 37.2, while the standard deviation is 22. What can we conclude from Chebyshev's theorem using k equals 2? So because we are interested in 2 standard deviations, we will look at the values 2 standard deviations above and below the mean. So we're going to take our mean and add 2 standard deviations. So we have 37.2 plus 2 times 22, which gives us 81.2. And 2 standard deviations below the mean. So we take the mean of 37.2 and subtract 2 of the standard deviations. 2 times 22 gives us negative 6.8. Now, because the age cannot be negative, we have a natural boundary where we'll have to consider this as 0. Therefore, by the theorem, we can say that at least 75% of the population of New Jersey is between 0 and 81.2 years old. Where did we get 75? Let's back up. We got that from using the formula. 2 standard deviations is talking about 75%. 3 standard deviations, 88.9 for any distribution shape. And then when we calculated the 2 standard deviations above and 2 standard deviations below, we got these values. The negative value doesn't make sense for age, which is why we're defaulting to 0. And we are concluding 75% of the population is between 0 and 81.2 years old. It is very doubtful that this revelation will become breaking news, just like when we talked about how range can sometimes not be useful. It might cover the entire data set. 0, a newborn, to 81.2, some people's life expectancy, doesn't really shed much light about the age spread in New Jersey. This concludes our measures of dispersion. See you next time.